I learned something new recently. I want to share it with you to correct something that was in one of my previous videos, which is about proof by contradiction. Proof by contradiction is one of the coolest ways of proving things that there is. There's proofs by deduction, induction. Proofs by contradiction is one of the most clever ways that there is to show that something is true. Okay, we don't tend to use it all that much in high school maths, which is a shame, I guess. And part of that is because it's quite confusing. Now, here's the way it works. Suppose you want to prove this statement. If P is true, then Q is true. Okay, now we come up with these kinds of statements all the time in maths. And so we usually would look at the given information, what you know about P, what you know about Q, and sort of progress linearly, naturally from P to Q, okay? And that's the way that most of us have learned to prove things, okay? The way that proof by contradiction works is to assume that the premise, what you're trying to prove, you assume that it's false. You assume the opposite, and then you work with that assumption, and then you'll show that there's some contradiction that results from the assumption you made. And so if there's some contradiction, that means your prior assumption at the beginning must have been wrong, and that means that your original statement, must be right, okay? Now, when you think about how do I assume the opposite of this, a natural way to think about it would be this. If P is true, then Q is false, or Q is not true. Now that looks like it's the opposite, and which is what I've said before. And I've since learned that's not the best way to say it. The real opposite of this statement up here is not this, but P is true and Q is false. Okay? Now you're like, that looks really, really similar to me, and they are very similar. The difference is just one word, in a sense. Here I have and here I have then. Okay? Now, if you want to go and have a look and study the difference between the logic implications between the differences there, then go ahead and do that. But the point is that there is a difference, okay? Now, to illustrate how that actually works, I'm going to show you a really cool proof, which I have over here. And I really like it because in some ways it's surprising, it's quite elegant when you do it as a proof by contradiction, and it also links together quite a few different parts of maths, okay? So let's have a look at it. Now, if two different numbers are positive and real, then their arithmetic mean is larger than their geometric mean. Now you're like, oh, what are all of those? Before I explain all of it, let me just point out to you that what you've got is these two terms, which probably the most natural way that they connect to, say, two-unit maths is series and sequences. You might recognize arithmetic and geometric from there. Okay. Then you also have this is larger than, so you're also bringing in the three-unit topic of inequalities. Okay. And so we're going to bring together these kinds of branches of maths and prove this statement by contradiction. Okay. Now this is all wordy. Okay. So how do I take this and put it into mathematical language? Well, first I have a condition, right? So this is my if P is true. Here's what I'm going to call P, right? Two different numbers are positive and real. Okay. So I'm going to say a couple of things there. Firstly, let's give these numbers names. So let's call them x and y. Okay. So if x and y are parts of the real number set and a positive, okay, the set of positive real numbers, okay, that's this part accounted for, and the numbers are different. They're two different numbers. Okay. So x does not equal y. Okay. So given that condition, I want to prove now. What is this stuff? Arithmetic mean, geometric mean. The whole idea is very easy to consider if I give you an example. Okay, so consider two numbers, 2 and 8. Okay, and I want you to imagine that there's some third number in between 2 and 8. Okay, and when I put them together, I'm going to get a sequence, a series of numbers. Okay, now depending on what number you put in here, you'll call it a different kind of series. For instance, if I were to put the number 5 in here, okay, 2, 5, 8. The kind of sequence I have here, the kind of progression, is an arithmetic progression because there's a common difference between the terms, okay? You add 3 each time. So we would call this an AP, an arithmetic progression, okay? Now what that means is we call 5 the arithmetic mean of 2 and 8. It's the number you stick between 2 and 8 to create an arithmetic progression. Okay. Now, you can go ahead and do the maths for this. You can think about what the individual terms of an AP are. But suffice it to say that the way you get 5 is by taking the average, that's another way of saying mean, right, of 2 and 8. So you're going to add them, 2 plus 8, and then you divide by 2. That's 10 on 2, which gives you the 5 that you expect. Okay. So if I've got not 2 and 8, but x and y, then the way to take the average, the arithmetic mean of those, is to add them and then divide by 2. That'll give me the arithmetic mean. Okay. Right. Now I want to say that the arithmetic mean is larger than, okay, now what's the geometric mean? You might be, working out what's going on here. If I take the same two numbers, 2 and 8, and I want to imagine another number in here, but instead of making an AP, an arithmetic progression, I want to make a GP, a geometric progression. Well, the number that's going to make this particular set of 3 numbers a GP will be 4, okay? Because then instead of going a common difference, plus 3 plus 3, I've got a common ratio, times 2 times 2, okay? Now, how did I get 4? Where did that come from? Apart from me just thinking, oh, that will work, okay? Well, if you take the product of these two numbers, 2 times 8, right? And then you take the square root. That's the square root of 16, which is 4, right? So 4 is the geometric mean of 2 and 8. It's the number you stick in between 2 and 8, and you'll get a GP, okay? So instead of 2 and 8, if I have x and y, I'm going to have the square root of xy, okay? That's here. Okay, so this is what I'm setting out to prove, this statement here, okay? If I've got this condition, then I want to prove this inequality, okay? So now that you know what we're trying to prove, arithmetic mean, geometric mean, how does a proof by contradiction make this happen? Okay, it's super clever. What you do is you assume the opposite of this statement. You assume the opposite, okay? Now I just established before that the exact opposite of this is x and y are real numbers and they're different, okay? There's 1/2. And now I'm going to assume that the opposite of this is true, okay? So all I have to do to make the opposite of that is turn the inequality around and add the boundary. So I would say this, x plus y on 2 is less than or equal to the square root of xy, okay? So equating this back to before, this is p is true and q is false. Because that's what q is really saying, okay? And this is the opposite of that, right? Okay, well, how am I going to do this? How am I going to go about doing this? I'm going to start from over here, start from this side, okay? I'm going to notice that in this inequality, okay, because x and y are both real numbers, okay? Therefore, the left-hand side, x plus y on 2, okay, that's going to be greater than 0, okay? It's also going to be a positive real number. And in the same way, the square root of xy, by definition, is also greater than 0. Okay? And I only know that these are true because they're both positive numbers. Okay? Now, since they're both positive numbers, for this inequality, I can square both sides and it'll work. The inequality sign won't turn around and I won't get different cases because I know they're both positive. Both sides are positive. Okay? Just like if I said to you, 3 is less than or equal to 5. They're both positive, so I can square both sides and it's still true. 9 is still less than or equal to 25. Okay, whereas if one of them is negative, you might be in trouble. Okay? Right, so having established that, I'm going to square both sides. Right? I'll get this, x plus y on 2 all squared is less than or equal to the square root of xy all squared. Okay, so far so good. Let's do a little bit of algebra to this, see if we can simplify it out a little bit. If I square the top there, I'm going to get x squared plus 2xy plus y squared all over 4. You've got to square the top and the bottom. Over here, naturally, you just get xy. Okay? I'll multiply that 4 across, so that gives me this. I've got 4xy here. And now I've got x, y's in common on both sides, so I'll collect like terms. That gives me this. Yes, okay. Now that's a perfect square. How do you factorize it? It's x minus y all squared. So let's say they're equal to 0, okay? And that's about as simple as it gets. I can't really go any further than that. And this follows directly from this statement, which I've assumed to be true, okay? So therefore, I'm going to say, sure, I'm going to go with that. I'm going to call that statement 1, okay? But that's what I got from this. I can get information from here too, okay? Think about this. X and y are not the same. X is not equal y. So I could subtract y from both sides and get the difference between x and y can't be 0, right? Because they're not the same number, right? And you see why I might do this. The reason why this is a useful thing to get is because I have an x minus y here, right? Okay, now hold on. I've assumed that they're both real numbers, right? One of the things about the real numbers is when you square them, you'll get something positive. If they're not real, if they're complex numbers, you've got no guarantees. You might square it and get something negative. But these are real numbers, right? So if I square both sides, or just square that number, really, remember it's not equal to 0. So this thing, it's a square number, it's got to be positive. It must be, right? No matter what values you stick in for x and y, so long as they're positive real numbers, if you subtract one and then you square it, you'll get something positive, okay? Now I'll call this statement 2. But hold on. Statement 1 and statement 2 are directly contradictory. They directly contradict each other. So therefore, I can say, look, I came from this assumption that this was true. But when I followed that through and thought about it, it ends up in something which doesn't make sense. Okay? So therefore, this cannot be true. This cannot be true. So the opposite of that is this inequality. Okay? So I can say, therefore, if they are positive real numbers that are different, then the opposite of this must be true. In other words, the inequality must go the other way, namely the way that it was facing when we started. Okay? So that's how you approach a proof by contradiction.